Hi, I'm Tim Pennings, Chair of the Math Department here at Davenport University, 2020, in case this is broadcast other years. And we just finished developing a new course called College Mathematics, which is Math120. And we've got a couple goals for that course. One is that for all you students who take it, to kind of know the foundational mathematics that's important for lots of stuff in the real world. Lines are really important. Parabolas are important for lots of things. Exponential functions, things that grow exponentially. Right now we're in the middle of the COVID, the whole pandemic virus, and the whole idea of exponential growth is just everyone is becoming aware of how important exponential growth is and what it means, flattening out the curves, things like that. So anyway, that's all important stuff. And so this course covers that, and then it also covers other just fun, interesting stuff in mathematics. And so about a third to half of the course is for that as well. So I think it's a great college course. And what this series of YouTube lectures is going to do is just to hit some of the basics of every section. It's not meant to fill out everything. You need to go to class for that, read the book, and go to your instructor's courses, to the classes. But this is meant maybe to be used as a review, or maybe as a something to do ahead of time, just to kind of get a sense of what's going on. Or if you happen to have to miss class, you could use it along with reading the material. So it's kind of a what's the word? Kind of a supplemental thing, which you can use along with the instructor's lecture and your time in class to learn the material all the better. So the first section that we're going to cover is 1.3. That's problem solving, and we're going to do that along with 8.1, and then you're going to be given some homework on that in class. And so I want to get you all geared up for that. George Polya, if you read the book, is a great mathematician who's named in this section. I actually have a George Polya award on my wall. I won an award for a math paper I gave, so I have special interest in some of the things that he suggested as far as problem solving. So anyway, I'm not going to repeat what's in the book. I want to do some of my own things. So turn off the video if you want in order to spend time on this, but this is a problem that's one of my favorites. Here you have a 3x3 grid of numbers, and the idea is of dots. And the idea is to try to connect all those dots using as few line segments as possible. And the line segments have to be connected. Otherwise, we could go boom, 2, 3, but those aren't connected. So for example, here would be one way to try it, to go like this, and then 2, 3, 4, and 5. And by the time I get to 5, I've connected them all. So I can't take my pen off the board. So that was one attempt, and I had 5. The question is, can you do it with less than 5? And so if we get rid of these and try it again, let's see once what happens. Let's go like this. Let's go 1, 2, 3, let's see, 4, 5, 6. There, it took 6 of them to do it. So that didn't help. I think it's easier to make the dots again. Let's try another one yet. One, 2, 3, 4, 5 there as well. So it seems like 5 are needed. Question is, can you do it with less? And I'm going to show you how to do it with less. So go ahead and turn off the video and see if you can do it on your own. I'm going to do it with 4, but see if you can do it on your own. This is a fun problem, and I'm going to do it right now. So if you haven't had time to play with it yet, don't miss out. Try to play with it on your own. So how about this? See if I can remember how to do it. 1, 2, 3, 4. See that? There I got them all. And the key was that I went out of the confines of the box. I thought outside the square, thought outside the box, very literally. And notice that I didn't tell you that you had to stay within the square, so your mind might have put that constraint on even without me telling you. So part of the solution, part of the way to do good problem solving is to just not put constraints on yourself, but try to think wild and creative, and think of all the possibilities. Think of what kind of constraints you are putting on the problem that aren't necessarily, don't have to be there. So anyway, that was a problem on a kind of an intelligence test that they gave for years and years, and then the right answer was supposed to be 4, but then some young kid realized that the answer was 3 instead. So this is really cool because all the experts thought it was 4, and then he said, no, it's 3. And what this young kid realized is that these were said to be dots rather than points. A point has just an infinitesimally small breadth to it, but a dot has some bigness to it, right? It has some size to it. So here's what this young guy said. He said, hey, let's do this. Let's get a line that goes through the top of this dot, the middle of this dot, and the bottom of this dot, and then goes out far enough. I'd have to go a little farther than this, and then come back and do the top of this one, the middle of this one, the bottom of this one, and go out far enough so that you come back, do the top of this one, the middle of this one, the bottom of this one. So that shows how even the experts who thought they had thought creatively and thought outside the box and had the right answer actually didn't have the right answer after all. And I'll let you decide if there's even a way to do better than this. Some people claim that there's a way to do it with just one line. And here's the way they do it. They say, well, okay, if I would take this piece of paper that this is on, or this board, and roll it into a cylinder by taking these two ends and rolling it together, then I'd have a cylinder like a piece of paper like this, and then I'd be able to basically take one line, and then I'd go all the way around and keep going around the back side, and this line would keep going like this, and eventually do this and keep going around the back side. Maybe I'd have a couple in between, but then come around like this again. So maybe even one line is possible. So anyway, it just shows creative thinking, okay? Here's another one I'm going to give you, again, which is not in the book, but is one of my favorite problems. You have a mathematician who visits a friend, and the friend says, I have three daughters, and the product of their ages, I'll just go A times B times C, A times B times C for the three daughters. The product is 36. And he says, can you tell me what the age of my daughters are? And the mathematician says, no. Says, not enough information. Not enough information. So then the friend says, well, okay, I'll give you some more information. He says, if you go and look at my house number on my house, the sum of the three ages adds up to my house number. Okay, that adds up to my house number. So the mathematician goes and looks at the house number, and he comes back and he says, that's still not enough information. Okay? And finally, the friend says, okay, I'll give you the last piece of information. My youngest daughter is a blonde. Youngest, they're all daughters. Youngest daughter is a blonde. And then the mathematician says, okay, now I know the ages of your daughters. And so that's a lovely problem, because it seems like, how in the world would this give you more information that would allow them to solve the problem? Okay? So again, if you want to, take this down and see if you can do it on your own before I do it for you here. It's one of my favorite ones. I love explaining it. It took me a while to figure it out myself. I think I did, and I felt real proud of myself when I did. Okay? So here's the first thing I finally did. I said, well, let's think of all the possible ways that you can get three ages to add up to 36, or I should say to multiply to 36. So you have to be pretty what's the word? Disciplined about it, form a pattern, organized, that's the word, organized about it, and get them all. So I'm going to start with as small numbers as I can over here. So 1 times 1 times 36, 1 times 2 times 18. These are going to be as small as possible. 1 times 3 times 12, that gives you 36. 1 times 4 times 9, that gives you 36. 1 times 6 times 6. So these are all ones, and these I started 1, 2, 3, 4, 6. And there's none larger than this because this number, notice, is always smaller than this one. I could have 1 times 9, but then that would be 4, which is that one. Okay? So now let's start with 2. 2, I don't need to go 2 times 1 because that's already here. So I'm going to go 2 times 2, that's 4. 4 times 9 is 36. Notice you have to know your multiplication tables. 2 times 3, that's 6. Times 6 is 36. 2 times 4, 2 times 5, 2 times 6. I think that's all you can do with 2's. Because, yep. So finally, how about 3? 3 times 3 is 9. 9 times 4 is 36. And then this is bigger than this, so there's no reason to go 3 times 4 times anything because I'm already bigger than 36. 1, 2, 3, 4, 5, 6, 7, 8. I think I've got them all there. Part of problem solving is thinking carefully through all the possibilities. So I think I've got them all. 4 times, yeah, okay. So there they all are. So now the question is, what do these add to? Okay, so he's talked about they added to his house number. So if we were to add these numbers, what would we get? This would be 38. These would be what? 21. This would add to 16. This would add to what? 10 and 4 is 14. This is 13. This is 9, 10, 11, 12, 13. This is 6, 7, 8, 9, 10, 11. And this is 10. So there's all the possible sums. And remember what happened? The mathematician said, I still don't have enough information. So now we have to think about it. If the house number were 38, he would know that this was the age of the daughters. If the house number had been 21, he would have known that this would have been the age of the numbers. He checked the house number and he came back and he said he didn't have enough information. If the house number had been 16 or 14 or 11 or 10, any of those, he would have known exactly what the ages were. But he came back and he said there wasn't enough information, so that must mean that there were 2 possibilities for how to get the house number. There's one way to get 13, there's the other way to get it. And so he said there's still not enough information. Now, can you see the end coming? His friend said, the youngest is a blonde. Okay, so by saying the youngest is a blonde, he was basically saying there is a youngest child. Here you have 2 that are both 2 years old, so presumably they must be twins, and so they're basically the same age. So by saying the youngest is a blonde, he was saying this is the way you got to the house number of 13, therefore their ages must have been 1, 6, and 6. Okay, isn't that clever? I love that problem because it again just takes creative thinking. I pondered it a while before I figured it out, and it's kind of cool. Here's one more that I'll give you. I'm not going to give you the answer to this one, but let you ponder it, and you can see if you can get it. Here's the question. There's 10 or 12, I should say. 12 billiard balls. Okay? One of them is a slightly different weight. One, I'll call it odd ball. And let me emphasize, you don't know whether the odd ball is light or heavy. You don't know. It could be either a little bit too light or it could be a little bit too heavy. You don't know. All you know is that one of them is different. Let me say different instead of saying odd. one different ball, different weight. Okay? And you've got a balance scale here, a balance scale that just determines which side goes up and which side goes down. And your charge is to find the different ball using balance scale just 3 times. Just 3 times. You can only use it 3 times, and using it only 3 times, you find the odd ball, and you don't know whether the ball is light or heavy. Okay? So again, I'll give you a moment to get started on it, and then Russell. This one took me about 3 days to figure. It took me a weekend to figure it out. Maybe it's easier for a bunch of you, but anyway, it took me a while, and I guess I won't give you any hints. I won't give you any hints. Just I'll let you figure it out. Okay? So my Davenport email is tpennings@davenport.edu. So feel free to write me for a hint if you want. Okay, so this is the first half of this section. Now I'm going to get into one other set of kind of fun problems, but I'll wait with that until the next video, just so that each video is kind of the right size.